Tonight, we follow the story of an asteroid as it travels through space and meets the surface of Earth. Welcome to the Orbit for Sleep channel. Let us follow the orbit of science and drift gently towards sleep. The sky changes without warning. A quiet blue vault that has held steady for millions of years is briefly altered by a moving point of light. At first, it looks no different from an ordinary star. It does not glow brighter. It does not announce itself. It simply grows, slowly, steadily, as it closes the distance between space and ground. Long before impact, the object has already been traveling through the solar system for millions of years. It is a fragment of ancient rock, shaped by collisions that occurred before Earth formed oceans. Its path is guided by gravity alone, pulling it into a steep and irreversible descent. As it enters the upper atmosphere, friction with air begins to strip away its outer layers. The surface heats rapidly, not because space is hot, but because air is suddenly forced to compress in front of an object moving faster than sound by dozens of times. At an altitude where aircraft normally fly, the asteroid is already generating temperatures hotter than most industrial furnaces. The surrounding air becomes plasma, a state of matter where air molecules are torn into charged particles. To an observer on the ground, the object now appears as a blazing fireball. The sound does not arrive yet. Light reaches the eye immediately, while pressure waves take longer to travel. Impact occurs when the asteroid reaches the surface at several kilometers per second. At that moment, motion becomes heat and pressure almost instantly. The kinetic energy, the energy of movement, converts into a shock wave that expands faster than any explosion created by human technology. Rock behaves like liquid under such extreme force. The ground does not resist in a familiar way. It flows, rebounds, and fractures at the same time. The first physical effect is not fire, but pressure. A compressed wall of air and debris surges outward in all directions. Buildings, trees, and terrain are struck by a moving front of force before flames arrive. This effect resembles the sudden pressure wave felt when standing too close to a thunderclap, but multiplied to an incomprehensible scale. Within seconds, thermal radiation follows. Heat spreads outward as infrared and visible light, igniting dry material and elevating temperature over a vast area. The rock at the impact point melts instantly. Some of it vaporizes, expanding upward into the sky before gravity pulls it back down. Tiny droplets of molten stone cool in midair and fall as glass-like particles. This sequence, pressure first and heat later, explains why impact destruction is often misunderstood. Popular imagery focuses on fire, but physics shows that shock is the dominant early force. The same ordering occurs in small, familiar events. When a heavy truck passes close by, the pressure change is felt before the sound fully arrives. An asteroid impact follows the same principles, only governed by planetary-scale energy. Scientists reconstruct these moments using a combination of crater measurements, laboratory shock experiments, and computer simulations. Data from past impacts, including those that formed large craters in North America and Eurasia, reveal consistent patterns in pressure distribution and material flow. These records allow the first seconds of collision to be understood with high precision, even though no human has ever witnessed such an event at close range. The moment the sky changes is therefore not defined by fire or noise, but by physics unfolding at extreme speed. Gravity guides the object, friction sculpts its entry, and energy reshapes solid ground into fluid motion. The same laws that govern a falling cup on a kitchen table also govern a rock striking a planet. The scale shifts, but the rules remain unchanged. From a distance, an approaching asteroid appears motionless against the background of stars. Its speed becomes noticeable only when measured across long intervals or compared to nearby objects. In reality, the body is moving through space at tens of kilometers per second, guided by the gravitational balance of the solar system. Small shifts in planetary gravity, especially from Jupiter and Earth, gradually shape its path over thousands or even millions of years. As the asteroid crosses the boundary between space and atmosphere, its environment changes abruptly. Space offers almost no resistance. Air, by contrast, behaves as a dense fluid at extreme speed. The leading surface of the asteroid forces air molecules to compress tightly in front of it. Compression raises temperature rapidly, even though the surrounding air was cold only moments earlier. This process is known as aerodynamic heating, and it is the same principle that heats spacecraft during re-entry. The outer layers of the asteroid begin to fracture and peel away. Smaller objects often disintegrate completely at high altitude due to internal cracks and unequal stress. Larger bodies remain structurally intact. The glowing trail visible from the ground is not the asteroid itself burning, but the surrounding air heated to incandescence. The rock is losing mass through ablation, a gradual erosion caused by extreme surface heat. During this descent, sound still lags behind the visible event. Light reflects instantly, while pressure disturbances require time to travel through air. This delay explains why observers often see a bright streak first and hear the sonic shock later. The same effect occurs during distant lightning strikes, where the flash arrives before the thunder. Impact begins when the remaining mass reaches the surface at hypersonic speed. The final seconds of travel are governed by inertia, the tendency of moving objects to stay in motion unless acted upon by strong opposing forces. The ground provides that opposing force with overwhelming intensity. Movement halts over a distance shorter than the length of a city block. Energy stored in motion becomes pressure and heat in a fraction of a second. From a physical perspective, this sequence, from silent approach to frictional heating to sudden arrest, follows strict mechanical rules. The asteroid does not explode due to internal combustion. Its destructive power arises from velocity alone. A familiar comparison can be found in daily life. A falling hammer delivers more force than a resting one. Not because its material changes, but because motion adds energy. An asteroid is a hammer accelerated by planetary gravity for millions of years. Astronomers reconstruct these approach paths using orbital tracking and mathematical modeling. By measuring repeated positions of near-Earth objects against distant stars, scientists calculate future trajectories with high accuracy. This method allows the slow approach of potentially hazardous objects to be studied long before atmospheric entry occurs. The silent phase of approach is therefore not invisible to science, even though it remains imperceptible to human senses. The transition from distant motion to sudden impact is shaped by gravity, air, and speed alone. Each stage unfolds predictably under physical law, transforming a quiet traveler of space into a brief but powerful planetary event. When an asteroid strikes Earth, the energy released is not produced by fuel, fire, or chemical reaction. It comes entirely from motion. This is known as kinetic energy. The energy an object carries simply because it is moving. The faster and heavier the object, the greater this energy becomes. Space provides an environment where speed can grow for millions of years without resistance. Typical impact speeds range from 15 to more than 25 kilometers per second. At these velocities, even a relatively small mass carries immense energy. When converted into familiar terms, a stony asteroid only a few hundred meters wide can release energy comparable to tens or hundreds of nuclear weapons detonating at once. Larger bodies scale far beyond this. The comparison is not used for drama, but for measurement, allowing scientists to relate cosmic events to human-built explosives. Unlike a nuclear device, however, the energy source is not stored inside the object. It is accumulated gradually as gravity accelerates the body along its orbit. For years, the asteroid moves silently through space, storing energy in the form of velocity. The release occurs only when motion is abruptly stopped by the planet's surface. Upon impact, this kinetic energy transforms almost instantaneously into heat, pressure, and mechanical deformation. Solid rock briefly behaves like fluid because the stress exceeds the strength of its atomic bonds. The temperature at the impact point rises to thousands of degrees in less than a second, hot enough to melt and partially vaporized stone. A useful, everyday comparison can be found in a simple car collision. At low speed, a car's motion causes minor damage. At high speed, the same vehicle releases enough energy to crumple steel and shatter concrete barriers. The material remains the same. Only the speed changes the outcome. An asteroid applies this principle on a planetary scale. This energy conversion also explains why impact effects extend far beyond the size of the asteroid itself. The object may be small compared to a mountain, yet the region affected can span entire cities or continents. Energy does not remain confined to the original mass. It propagates outward as shock waves through air, ground, and rock. Scientists quantify these energies using basic mechanical equations tested in laboratories and confirmed by decades of observation. Crater sizes, melted rock layers, and seismic records allow past impacts to be reconstructed with reliable accuracy. The numbers consistently confirm the same conclusion. Motion alone, when scaled to cosmic speeds, becomes a force that rivals the most powerful technologies ever created by humans. The first seconds after an asteroid strikes are defined by extreme pressure rather than fire. At the moment of contact, the object's remaining velocity is forced to zero over a very short distance. This sudden deceleration generates a compression wave that travels outward through both ground and air at tremendous speed. The surface beneath the impact does not behave as solid rock in the ordinary sense. Under these conditions, it flows like a dense liquid. A hemispherical shock wave moves through the crust, crushing and fracturing rock layers that may be billions of years old. Above ground, a matching pressure front expands through the atmosphere. Air is pushed outward faster than sound, forming a blast similar in structure to that of a massive explosion, but driven entirely by mechanical impact rather than combustion. Within the first second, temperatures at the impact point rise to several thousand degrees Celsius. Rock melts instantly. Some material is vaporized, changing directly from solid to gas. This vapor expands violently upward, carrying molten droplets with it. As gravity begins to pull this material back down, it cools in midair and later settles as fine glassy particles across the surrounding region. Light from the flash arrives before any audible sound. Observers at a distance would see intense brightness long before hearing the shock. This delay is caused by the difference between the speed of light and the much slower speed of sound in air. A familiar version of this effect appears during fireworks, where the flash is seen first and the sound follows later. The ground response continues to evolve even after the initial contact ends. Rebound motion lifts sections of the crust upward, forming the central structures seen in large impact craters. At the same time, concentric rings of fractured rock spread outward. These patterns are not random. They follow predictable stress distributions that engineers and geophysicists measure using controlled impact experiments and seismic data. During these first seconds, gravity, inertia, and material strength determine every outcome. Flames and long-term environmental effects emerge later. The immediate aftermath is governed almost entirely by pressure, deformation, and heat transfer. These forces operate according to the same physical laws that bend steel in industrial presses or compress air in a piston engine, only scaled to a level rarely encountered on a planetary surface. By studying high-speed laboratory impacts and comparing them with real craters preserved on Earth and other planetary bodies, scientists have reconstructed these early moments with increasing precision. The first seconds after impact represent one of the most extreme mechanical environments that natural physics can produce on a solid world. The destruction caused by an asteroid impact does not spread like a slow wave across the landscape. It expands at extreme speed from the very first instant. The initial shock front travels outward through air and ground faster than sound, carrying compressed matter and energy at supersonic velocity. This expansion defines the physical reach of the earliest damage. Within the first few seconds, the pressure wave races outward across tens of kilometers. Near the impact point, structures are crushed by direct overpressure. Farther away, the same wave arrives as a powerful blast of moving air that can still flatten buildings and not root trees. The speed of this front depends on the energy of the impact and the density of the atmosphere. But in all large events, it exceeds any storm, explosion, or wind system observed in human history. Following closely behind the pressure wave is the thermal front. Heat propagates more slowly than shock, but still spreads rapidly as intense radiation. Dry vegetation, exposed materials, and surface infrastructure absorb this energy and ignite if conditions allow. The separation between pressure and heat often measures only a few seconds, but the physical processes remain distinct. The ground transmits destruction differently. Seismic waves move outward through the crust at several kilometers per second. These waves reflect and refract through different rock layers, sometimes re-emerging far from the original crater. In past impacts, measurable ground motion has been detected thousands of kilometers from the strike location. The Earth behaves like a connected, elastic body, even during violent disruption. A simple daily comparison helps illustrate this expansion of force. When a heavy door is slammed, the vibration is felt immediately through the frame and nearby walls, even before sound fully fills the room. An asteroid impact applies the same principle on a planetary scale. Energy does not remain at the point of contact. It must travel. Scientists estimate the outward reach of destructive pressure using fluid dynamics and solid mechanics, the same branches of physics used to study explosions and earthquakes. Data from historic and prehistoric craters confirm that damage radius increases roughly with the cube root of released energy. This mathematical relationship explains why doubling impact energy does not merely double destruction, but expands it dramatically. The speed of destruction, therefore, reflects not chaos, but orderly physical propagation. Shock waves, thermal radiation, and seismic motion each carry energy outward along well-defined paths. Their velocities differ, but together they form a coordinated expansion that reshapes the surface over vast distances in less than a minute. Shock waves are the primary carriers of force immediately after an asteroid impact. These are not ordinary sound waves. A shock wave forms when pressure changes so abruptly that air and solid material cannot adjust smoothly. Instead, matter is compressed almost instantaneously, creating a moving wall of extreme pressure that travels faster than normal sound. In the atmosphere, this shock front behaves like a rapidly expanding dome. Air molecules are forced tightly together, raising both pressure and temperature in a fraction of a second. Objects caught within this front do not experience a gradual push. They are struck by a sudden mechanical load that exceeds the strength limits of wood, steel, and concrete. This is why structural failure occurs so widely, even before flames arrive. Through solid ground, shock propagation follows different physical rules. Rock transmits compression much more efficiently than air. The impact sends intense stress waves downward and outward through the crust. At these pressures, brittle rock temporarily loses its rigidity and deforms plastically, behaving more like thick fluid than solid stone. Layers that formed over geological time are compressed, fractured, and in some regions completely overturned. Laboratory experiments reproduce these effects using gas guns and high-energy impact devices. Small projectiles striking metal or rock plates at extreme speeds generate miniature shock fronts that mirror those created by asteroid collisions. Sensors record pressure, temperature, and deformation at microsecond resolution. These controlled results closely match patterns observed in large natural craters on Earth and the Moon. A familiar everyday example of shock behavior appears during a supersonic aircraft path. The sudden pressure jump, known as a sonic boom, is a diluted form of the same physics that governs impact shock waves. In an asteroid event, the difference lies only in scale, not in principle. As the shock waves move outward, they weaken with distance, but remain destructive over vast areas. Reflections from subsurface rock layers can focus energy back toward the surface, intensifying damage unpredictably in certain regions. This complex interaction between air shock and ground shock contributes to the uneven pattern of destruction seen around large craters. Shock waves therefore act as the initial mechanical framework of an impact event. They shape both atmospheric blast and subsurface damage, linking the behavior of air and rock into a single, continuous physical response driven by extreme compression and rapid energy transfer. When an asteroid strikes the surface, the ground does not simply break outward to form a hole. Crater formation is a dynamic process involving compression, flow, collapse, and rebound. The final shape, seen from above, is the result of several overlapping stages that unfold within minutes, not hours. During the first instant of contact, rock beneath the impact point is forced downward and outward under extreme pressure. This stage is known as the compression phase. Material behaves like a dense fluid as stress overwhelms the strength of crystal bonds. Rock layers that formed over billions of years are momentarily treated as if they were soft clay. This is followed by the excavation phase. Shocked material is driven upward and outward in a broad curtain of debris. The outward flow carves the initial cavity, ejecting rock at high speed along ballistic paths. Larger fragments fall near the crater rim, while fine particles can be carried far beyond the visible boundary. After the outward motion slows, gravity reshapes the cavity through collapse and rebound. The central floor, which was driven downward during compression, springs back upward due to elastic recovery of the crust. This rebound forms the central peaks seen in large, complex craters. At the same time, the steep crater walls become unstable and slump inward, widening and smoothing the final structure. A familiar daily comparison can be observed when a heavy object is dropped into soft sand. The sand splashes outward, then partially collapses back toward the center. The rebound is gentle and slow. In an asteroid impact, the same principle operates, but the pressures are so large that solid rock replaces sand as the flowing material. The size and shape of the finished crater depend on impact, velocity, angle, and the mechanical properties of the target ground. Low-angle impacts tend to produce elongated structures, while near-vertical strikes form more symmetrical balls. Hard crystalline rock responds differently from layered sediment. By measuring crater diameters, rim heights, and central uplift structures on Earth, the Moon, and Mars, scientists reconstruct the energy of past collisions with high reliability. These geometric records preserve the mechanical history of impacts long after heat has faded and debris has settled. Craters therefore act as frozen signatures of both violence and order in planetary physics. Thermal radiation is one of the fastest agents of change following an asteroid impact. Unlike shock waves, which require air or solid material to travel through, thermal radiation moves outward as electromagnetic energy. It spreads at the speed of light and begins affecting the surrounding environment almost immediately after the first compression phase. At the impact point, temperatures rise to several thousand degrees within a fraction of a second. Rock melts, and some material vaporizes. This superheated zone becomes a source of intense infrared and visible radiation. Heat flows outward not by contact, but by direct energy transfer through space and air. Materials exposed to this radiation respond according to their physical properties. Dry vegetation, paper, cloth, and certain building materials absorb heat rapidly and may ignite if their ignition temperature is reached. Metals heat more slowly, but even steel can lose structural strength when exposed to sufficient thermal flux. A familiar daily example helps clarify this process. When standing near a campfire, warmth is felt even without touching the flames. The heat travels as radiation from the burning wood to the skin. An asteroid impact creates a similar mechanism on a vastly amplified scale, with the impact site replacing the fire as the radiant source. Thermal effects also interact with material already in motion. Debris ejected upward during crater excavation absorbs heat while airborne. As molten droplets cool, they form glass-like particles that later settle across wide regions. These deposits provide direct physical evidence of past thermal environments at impact sites. Scientists estimate thermal output using infrared radiation models originally developed for blast physics and industrial furnace design. By comparing melted minerals and heat-altered rock layers in known craters, researchers reconstruct the temperature distribution with increasing accuracy. Thermal radiation therefore acts as a rapid, invisible driver of ignition and material transformation, while shock waves, shape, structure, and pressure defines motion. Radiant heat quietly determines what burns, what melts, and what permanently changes at the molecular level in the moments following impact. When an asteroid strikes Earth, the impact does not affect only the surface. A powerful system of seismic waves travels outward through the crust and into the planet's interior. These waves are generated by the sudden transfer of momentum from the moving asteroid to the stationary ground. Seismic waves from an impact include both compressional waves, which squeeze and expand rock in the direction of travel, and shear waves, which move material side to side. These are the same fundamental wave types produced by earthquakes, but the initial energy input from an asteroid can exceed that of most natural seismic events. The waves propagate at several kilometers per second, passing through different rock layers with changing speed and direction. Dense, rigid rock transmits waves faster than soft sediment. When waves meet boundaries between layers, part of the energy reflects while part refracts, bending into new paths. This behavior explains why shaking intensity varies unpredictably with distance from the crater. A simple, everyday analogy appears when tapping one end of a long table. The vibration travels through the wood and can be felt at the far end almost instantly, even though the hand never touches that area directly. An asteroid impact applies the same principle on a planetary scale. In large prehistoric impacts, seismic energy traveled across entire continents. Geological records show disturbed rock formations, fault reactivation, and secondary landslides occurring far beyond the original crater zone. These effects confirm that the Earth responds as a connected elastic body rather than as isolated surface regions. Modern scientists reconstruct ancient impact earthquakes by analyzing disturbed sediment layers, tilted strata, and shock-altered minerals. Computer models based on elastic wave physics allow the original impact energies to be estimated from these geological fingerprints. Seismic waves therefore serve as the deep interior signature of an asteroid strike. While shock waves dominate the atmosphere and thermal radiation reshapes the surface, seismic motion quietly transmits the event through the planet itself, linking surface collision to internal Earth dynamics. At the center of a large asteroid impact, temperatures rise high enough to melt solid rock within fractions of a second. Minerals that normally remain stable for billions of years lose their rigid structure and enter a liquid state. This molten material is not produced by fire or combustion, but by mechanical energy converted directly into heat. As shock and heat act together, multiple phases of matter appear at once. Some rock melts into liquid, some vaporizes instantly into gas. Other material remains solid, but becomes structurally altered at the atomic level. The coexistence of these states within a single event is one of the defining physical features of impact environments. Molten rock is ejected upward during crater excavation. As these droplets travel through the air, they cool rapidly and solidify before reaching the ground. The result is the formation of natural glass. These glassy particles often appear as small, rounded beads or thin sheets, depending on cooling speed and chemical composition. A familiar, everyday comparison can be seen when molten sugar is dripped onto a cold surface. The liquid spreads briefly, then hardens into a glossy, brittle solid. Impact glass forms through the same physical principle, but at temperatures thousands of times higher and across regions that can span entire landscapes. One well-known type of impact glass is tektite, found on several continents in distinct geographic fields. Their distribution patterns reveal both the direction and energy of ancient impacts. Another form appears as fused sand and rock within crater walls, where surface material was melted in place and rapidly quenched. Scientists identify these materials using spectroscopy and microscopic crystal analysis. Melted minerals display distinct chemical signatures, including the presence of shocked quartz and high-pressure crystal phases that do not form under normal geological conditions. These features allow impact events to be distinguished clearly from volcanic activity. The formation of molten glass therefore marks the moment when solid planetary crust briefly behaves like liquid and gas under extreme energy input. Long after pressure waves fade and craters erode, these transformed materials remain as physical records of the fleeting high-temperature environment created by asteroid collisions. Asteroid impacts have repeatedly reshaped the history of life on Earth. These events do not act only as agents of destruction. They also reorganize ecosystems, alter evolutionary pathways, and reset environmental conditions on a global scale. The physical mechanisms begin high in the atmosphere and extend into the oceans and biosphere. Fine dust and vaporized rock injected into the sky reduce incoming sunlight. Surface temperatures drop, photosynthesis slows, and food chains weaken from their foundation. The effect resembles a prolonged global twilight rather than an immediate freeze. At the same time, chemical changes alter soil, water, and air. Nitrogen oxides generated by heated air fall as acidic rain, soot and impact debris blanket land and sea surfaces. These combined stresses place sudden selective pressure on living organisms. Species adapted to stable climates struggle, while others capable of tolerating darkness, cold, or scarce food gain advantage. A familiar everyday comparison can be seen after large wildfires. When dense smoke blocks sunlight for weeks, plant growth slows and animal behavior shifts. An asteroid impact produces a similar reduction in light, but on a planetary scale and for much longer duration. Fossil records reveal several periods in which large numbers of species disappeared in a relatively short geological interval. In each case, layers of impact debris coincide with abrupt biological transitions. These connections provide measurable evidence that impacts have acted as global biological turning points rather than isolated regional disasters. Life does not end uniformly across all environments. Deep oceans, underground habitats, and organisms with dormant life stages often persist through the harshest intervals. After conditions stabilize, surviving species spread into emptied ecological niches. Evolution accelerates during these recovery phases, producing new forms adapted to transformed environments. The reshaping of life by asteroid impacts therefore reflects a balance between physical disruption and biological resilience. Extinction removes existing occupants of ecological space, while recovery allows innovation. Over geological time, this repeated pattern contributes to the diversity and structure of the biosphere observed today. Around 66 million years ago, a large asteroid struck what is now the Yucatan Peninsula in present-day Mexico. This single event is strongly linked to the extinction of the non-avian dinosaurs and a large fraction of life on Earth. The evidence for this impact is preserved in a global geological layer rich in the rare element iridium. The object is estimated to have been about 10 to 15 kilometers in diameter. When it struck the shallow ocean, it released an amount of energy equivalent to billions of nuclear devices. A crater more than 180 kilometers wide, now known as the Chicxulub crater, formed within minutes beneath sediment and seawater. The immediate effects were regional devastation from shock waves, earthquakes, and thermal radiation. Far beyond the impact zone, the more severe consequences unfolded through the atmosphere. Vast quantities of dust, sulfur compounds, and vaporized rock were injected high into the sky. Sunlight reaching the surface was sharply reduced for months to years. With light suppressed, global temperatures fell, and photosynthesis nearly collapsed. Plant growth declined on land and in the oceans, weakening the entire food web. Large animals with high energy demands, including most dinosaurs, could not survive the prolonged scarcity. Smaller animals, scavengers, borrowers, and organisms with slower metabolisms had higher survival rates. A familiar everyday analogy can be seen during extended volcanic winters when ash clouds temporarily cool global climate and dim sunlight. The Chicxulub impact produced a similar effect, but with far greater suddenness and scale. Geological layers from this period show a sharp boundary marked by shocked minerals, glass spherules, and chemical anomalies. Above this boundary, dinosaur fossils vanish almost completely. Below it, they remain abundant. This abrupt transition provides one of the clearest cause and effect records in Earth history. The extinction of the dinosaurs opened ecological space for mammals and other surviving groups to expand and diversify. Over millions of years, this biological reorganization reshaped terrestrial ecosystems, and eventually allowed primates and humans to emerge. The Chicxulub impact, therefore, stands as a defining example of how a single cosmic collision redirected the long-term course of life on Earth. After a major asteroid impact, the most persistent global effect is not the initial blast, but the long-term alteration of climate. The physical driver of this change is the massive injection of dust, aerosols, and vaporized material into the upper atmosphere. Fine rock particles and sulfate compounds can remain suspended in the stratosphere for months to years. Unlike lower atmospheric dust, these high-altitude aerosols are not easily removed by rain. They scatter and reflect incoming sunlight back into space, reducing the amount of solar energy that reaches the surface. As sunlight weakens, surface temperatures fall. This cooling does not occur uniformly. Continental interiors cool faster than oceans because water stores heat more effectively. Seasonal temperature contrasts intensify, stressing plant and animal populations adapted to stable conditions. Photosynthesis declines as light levels fall. On land, plant growth slows. In the oceans, microscopic algae that form the base of marine food webs reduce their productivity. With less primary production, energy transfer through ecosystems weakens at every level. A familiar short-term comparison appears after large volcanic eruptions. When ash and sulfur aerosols reach the stratosphere, global temperatures can drop measurably for several years. The asteroid-driven version of this process is similar in mechanism, but far greater in magnitude and spatial extent. Climate models based on fluid dynamics and radiative transfer indicate that severe cooling after large impacts can persist for years, followed by gradual recovery as atmospheric particles settle. In some cases, warming trends may later follow due to greenhouse gases, such as carbon dioxide released from heated rock and wildfires. Geological records preserve these changes in ice cores, sediment layers, and fossil assemblages. Shifts in isotope ratios reveal abrupt temperature changes. Sudden turnovers in species composition reflect ecosystems adapting to altered climate conditions. Impact-driven climate change therefore unfolds in distinct stages: rapid atmospheric loading, global cooling, biological stress, and slow recovery. This sequence links a brief cosmic collision to environmental transformation lasting far beyond the moment of impact itself. If a medium to large asteroid were to strike near a modern city, the sequence of damage would be governed by the same physical processes observed in natural impacts, but filtered through complex human infrastructure. The earliest destructive force would be the atmospheric shock wave. Within seconds of impact, a rapidly expanding pressure front would sweep across urban terrain. Buildings would experience extreme overpressure that exceeds their structural design limits. Glass would shatter first, followed by progressive failure of walls and load-bearing frames. High-rise structures would not collapse uniformly, but would twist and shear as stress travels unevenly through steel and concrete. Electrical systems would fail almost immediately. Power lines would snap under mechanical load, substations would be damaged by vibration and heat, and communication networks would lose synchronization. The modern city depends on continuous electrical flow, and its interruption alone would trigger secondary system breakdowns far beyond the initial blast zone. Thermal radiation would follow the shock wave. Exposed materials such as vehicles, rooftops, and surface infrastructure would heat rapidly. Fires would ignite in scattered locations rather than as a single continuous front. Fire suppression systems would be impaired by loss of water pressure and electrical control. A simple daily analogy can be drawn from large urban blackouts caused by storms. Even without physical destruction, transportation, healthcare, and logistics are sharply disrupted for days. An asteroid impact would combine electrical failure with widespread structural damage, magnifying the effect far beyond any weather-driven event. Air quality would degrade as dust, smoke, and fine debris fill the lower atmosphere. Visibility would drop and respiratory stress would increase. Movement of emergency vehicles would be slowed by debris-blocked roads and collapsed transport corridors. In coastal cities, secondary effects would include impact-generated tsunamis if the strike occurred offshore. Harbor infrastructure, seawalls, and port facilities would be especially vulnerable to combined pressure and wave forces. The response of a modern city to an asteroid strike would therefore reflect not only physical destruction, but also the failure of tightly interconnected technological systems. Urban environments amplify the consequences of natural forces because so many life-sustaining processes depend on uninterrupted mechanical and electrical continuity. Human survival in the first weeks after a major asteroid impact depends less on the initial blast and more on access to air, water, food, and stable shelter. Once the shock waves and heat pass, the dominant challenges become environmental disruption and systems failure rather than direct mechanical force. Air quality deteriorates rapidly as fine dust, ash, and chemical aerosols remain suspended. Breathing becomes difficult, especially for vulnerable populations. Water supplies are threatened by both physical damage to distribution networks and contamination from surface debris. Rivers, reservoirs, and treatment facilities can be overwhelmed by sediment and disrupted power. Food availability declines as transportation systems fail. Modern supply chains rely on continuous fuel delivery, refrigeration, and digital coordination. When these break down, grocery inventories empty within days. Agriculture cannot immediately compensate, especially under reduced sunlight and unstable climate following a large impact. A familiar everyday parallel appears after major hurricanes or earthquakes, when power outages and blocked roads interrupt normal life for weeks. In those cases, external assistance often arrives quickly. After a large asteroid impact, however, disruption may extend across entire continents, limiting the speed and scale of coordinated aid. Medical systems face severe strain. Hospitals depend on electricity, sterile water, and steady supply delivery. Injury from debris, fires, and exposure rises sharply while treatment capacity falls. Long-term health risks increase as air quality worsens and sanitation systems fail. Shelter becomes a central determinant of survival. Buildings that remain structurally intact provide protection from temperature swings, falling debris, and airborne particles. Improvised shelter offers limited defense, but can reduce direct exposure when permanent structures are unavailable. Historical data from large natural disasters combined with impact simulation models, show that survival rates correlate strongly with infrastructure resilience rather than proximity to the impact alone. Communities with redundant power systems, decentralized water access, and stored supplies recover more effectively. The first weeks after an asteroid strike, therefore, represent a transition from acute physical destruction to prolonged environmental and logistical stress. Survival becomes a matter of maintaining breathable air, drinkable water, usable shelter, and basic medical care under conditions where normal technological continuity has been sharply reduced. Asteroid impacts are often imagined as rare, almost mythical events. In reality, they occur across a wide range of sizes and frequencies. The rate depends strongly on the diameter of the incoming body. Small objects enter Earth's atmosphere daily, while large, globally significant impacts are separated by vast spans of time. Objects only a few meters across burn up harmlessly in the atmosphere every day, producing bright fireballs that rarely reach the ground. Bodies tens of meters wide strike far less frequently, on the order of once every few decades to centuries. These can cause regional damage, as demonstrated by the airburst over Siberia in 1908, which flattened forests across thousands of square kilometers without leaving a large crater. Asteroids, hundreds of meters across, are far rarer, typically impacting on timescales of hundreds of thousands to millions of years. These are the size class capable of causing continent-scale environmental effects. Kilometer-scale impacts, like the events linked to the extinction of the dinosaurs, occur on even longer geological intervals, often separated by tens of millions of years. A simple everyday analogy helps clarify this distribution. Minor car accidents happen frequently in any large city. Catastrophic multi-vehicle collisions are far less common. Planetary impacts follow a similar statistical pattern, where small events dominate in number and extreme events dominate in consequence. Astronomers estimate these frequencies using crater counts on Earth, the Moon, and Mars, combined with modern surveys of near-Earth objects. The Moon, lacking erosion and active plate tectonics, preserves impact records over billions of years. By comparing crater densities across different planetary surfaces, scientists infer how impact rates have changed through deep time. Modern sky surveys now catalog hundreds of thousands of asteroids and continuously refine these statistical models. While precise prediction of any single impact far in advance remains difficult, the overall frequency of different size classes is known with increasing reliability. Asteroid impacts, therefore, occupy a middle ground between random disaster and predictable natural process. They do not occur often on human timescales at the largest sizes, yet over geological time, they become an inevitable part of planetary history, shaping surfaces, atmospheres, and the evolution of life. Tracking potentially dangerous asteroids begins with repeated, wide-field observation of the night sky. Modern survey telescopes scan large areas using digital detectors that record the positions of millions of stars and moving objects each night. By comparing images taken hours or days apart, astronomers identify faint points of light that shift against the fixed background of distant stars. Once a moving object is detected, its orbit is calculated using classical mechanics. Each new observation refines the estimate of its future path. Gravity from the Sun, Earth, and other planets subtly alters the trajectory over time. Even small uncertainties in early measurements can grow, which is why long-term tracking requires continuous data collection. Near-Earth objects are classified according to how closely their orbits approach Earth's path around the Sunday. Those that pass within a defined distance threshold are monitored more closely. Probability calculations are updated whenever new positional data becomes available. These probabilities are not guesses, but statistical outputs based on orbital dynamics. A familiar everyday analogy can be found in traffic prediction systems. A single GPS position gives limited information, but a sequence of positions reveals speed, direction, and likely future route. Asteroid tracking operates on the same principle, using repeated measurements to convert isolated points into a reliable forecast. Several international programs contribute to this effort. Ground-based optical surveys locate most objects, while radar facilities provide precise distance and velocity measurements when asteroids pass close to Earth. Radar data greatly improves orbital accuracy by reducing positional uncertainty. Space-based telescopes add another layer of detection. By observing in infrared wavelengths, they identify dark asteroids that reflect little visible light. These objects can be difficult to detect with optical telescopes alone, but emit measurable heat as they absorb sunlight. Tracking does not prevent impact by itself. Its primary function is time. Early detection extends the available response window from days to years or even decades. This advanced knowledge transforms a sudden natural hazard into a long-term engineering and policy challenge rather than an unavoidable surprise. Deflecting an incoming asteroid is not a concept limited to science fiction. It is a measurable engineering problem governed by momentum, math, and time. The central principle is simple. A very small change in an asteroid's velocity, applied early enough, can shift its future position by thousands of kilometers. The most widely tested method is the kinetic impactor. A spacecraft is directed to collide with the asteroid at high speed, transferring a small amount of momentum. This does not destroy the object. It nudges its orbit slightly. In 2022, the DART mission successfully demonstrated this principle by altering the orbital period of a small moon of a binary asteroid system. Other proposed methods rely on continuous, gentle forces rather than sudden impact. A gravity tractor spacecraft would hover near the asteroid for months or years. Its own gravitational pull, although weak, would slowly draw the asteroid into a new trajectory. The effect is subtle but predictable if sufficient time is available. Solar radiation can also be used as a tool. By altering the surface of an asteroid with reflective material or controlled heating, the pressure from sunlight can be changed. Over long timescales, this tiny force can produce meaningful orbital drift. This method relies on the same physical principle that allows light to push spacecraft equipped with solar sails. A familiar everyday analogy can be seen when gently steering a large ship. A small change in the rudder angle produces little immediate effect, but over long distances, it leads to a completely different destination. Asteroid deflection operates on the same logic of gradual trajectory correction. More energetic proposals, including the use of nuclear devices, have been studied at a theoretical level. These approaches aim to alter velocity through rapid energy release near the surface rather than by direct destruction. They remain subjects of modeling and policy discussion due to their technical and political complexity. Successful deflection depends far more on early detection than on force. With years of warning, even modest technologies are sufficient to prevent impact. With only weeks or months, options become sharply limited. Planetary defense, therefore, transforms a natural hazard into a problem of preparation, coordination, and applied physics, rather than unavoidable fate. Earth is often imagined as a fixed target waiting for incoming objects from space. In reality, it moves through the solar system at nearly 30 kilometers per second, while the entire solar system orbits within the Milky Way. Asteroid impacts therefore occur within a complex, multi-layered pattern of motion rather than against a stationary backdrop. Asteroids themselves follow their own dynamic paths. Most originate in the main asteroid belt between Mars and Jupiter, where gravitational interactions slowly shift their orbits over long timescales. Repeated gravitational encounters, especially with Jupiter, can redirect some bodies inward toward the inner planets. When Earth encounters one of these shifting paths, the collision is not one of pursuit, but of crossing trajectories. Both bodies arrive at the same point in space, at the same time due to gravitational timing rather than direct aiming. This is why impact probabilities depend on orbital geometry as much as on object size. A familiar daily analogy appears at busy road intersections. Two cars traveling at steady speed may collide not because either targeted the other, but because their routes happen to intersect at the same moment. The motion of Earth and asteroids follows the same principle of intersecting paths within a moving system. The solar system itself is not isolated. It travels around the center of the Milky Way at roughly 220 kilometers per second. Over millions of years, this galactic motion alters the background environment through which the Sun and its planets pass, exposing them to varying gravitational fields and interstellar conditions. Impact risk is therefore shaped by layered motion. Asteroid orbits within the Sun's gravity, planetary motion within the solar system, and the solar system's motion within the galaxy. No single frame of reference remains fixed for long. Understanding Earth as a moving target reframes asteroid impacts as encounters within an active cosmic traffic system rather than strikes from a static sky. Planetary surfaces record the outcome of this long-term celestial motion as a history written in craters across worlds. Planetary impacts do more than scar surfaces with craters. They alter the long-term direction of worlds. Through repeated collisions, planets acquire their surface chemistry, atmospheric composition, and biological potential. In the early history of the solar system, impacts were far more frequent than they are today. Young Earth grew in part through continuous collisions with smaller bodies. These impacts delivered water, carbon compounds, and metals that later became essential for oceans, climate regulation, and life. Without this early bombardment, Earth would have remained a dry, chemically poor world. Later impacts acted not as builders, but as regulators and reset mechanisms. By stripping portions of atmosphere, reheating crustal layers, and triggering mass extinctions, they periodically restructured planetary environments. Each restructuring changed which physical and biological pathways were possible afterward. A familiar everyday comparison can be found in large forest disturbances caused by storms or fires. Destruction removes existing structures, but it also reshapes the conditions for new growth. On planetary scales, impacts perform the same role, simultaneously erasing and creating environmental opportunity. On airless bodies such as the Moon and Mercury, impacts dominate surface evolution almost entirely. With no weather or active tectonics to erase craters, the visible surface becomes a near-permanent record of collision history. On Earth, erosion and plate motion obscure this record, but the underlying influence remains. Across the broader universe, impacts appear to be a common feature of rocky worlds. Observations of debris disks around young stars and cratered surfaces on distant planets suggest that planetary systems everywhere undergo similar phases of collision and stabilization. The fate of a world is therefore not determined solely by its distance from a star or the composition of its atmosphere. It is also shaped by the random but statistically inevitable sequence of impacts it experiences over billions of years. These encounters link the quiet motion of cosmic debris to the long-term evolution of planets, climates, and life itself.